All right, so we've talked about inference procedures for proportions, and we've also discussed a one sample t-interval for mu. We're going to go ahead and look today at a one sample t-test for mu. So now we're going to do our significance test. So our learning targets for this one is to check those three conditions as always, calculate a standardized test statistic, but this time we're going to be using t instead of z, and a p-value, and then perform that significance test. Use that to make a conclusion. All right, let's go ahead and jump right into it because we already know how to do significance tests. So let's just put these pieces together in an example. Suppose you want to perform a test of h sub 0 being mu equals 5 versus your alternative hypothesis, which is mu is not equal to 5, at the alpha equals 0.01 significance level. A random sample of size n is 37 from the population of interest yields an x bar of 4.81, that's our sample mean, and a sample standard deviation of 0.365. Assume that the conditions for carrying out the test are met. Explain why the sample result gives some evidence for the alternative hypothesis, and calculate the standardized test statistic and p-value. So why does our sample result give some evidence? Because my sample mean is 4.81, which is not equal to 5, right? My alternative is that mu is not equal to 5. So I already have some evidence from my sample mean. So this is always our starting point. This is just to go back to the point of our significance test. This is what we're doing. I run a sample and I get a number that says like, I actually don't think that the mean is 5. We can't just go off of that with one sample, so we're going to run a test to see, did I get a correct sample value? If I did this a lot, if I did a lot of samples, would I get a number that's not 5? It's saving us from actually finding all of those samples. We're going to see if I even need to do all those samples or if this one was just a weird one. Let's go ahead and take a look at calculating our standardized test statistic and p-value next. All right, so we're going to draw our t-distribution. It looks a lot like a normal distribution, except it doesn't have that whole 1, 2, 3 standard deviations away from the mean kind of situation. But either way, we're going to look at show it as a curve, and then let's go ahead and calculate it. A test statistic is always my value minus the mean, or a statistic minus the parameter over my standard error, right? Which is this formula, which is going to be your S sub x over the square root of n, which we saw in the confidence interval formula. It's the same thing, right? So that's where we get our pieces. We have our statistic minus the parameter over the standard error. So I have 4.81, that's my statistic, that's my x bar. We have the parameter, which is the number that we always use in the hypotheses. And then we have our standard error, sample standard deviation divided by the square root of my sample size. So I get negative 3.17 as my t with a degrees of freedom of 36. Remember, we do 37 minus 1. So here's my test statistic. I have t equals negative 3.17. Let's go ahead and see how to use it with a table. So in table B, we're going to be going to our degrees of freedom section, which is 30, because remember, we just round down to the nearest one since there is no 36, so we're going to round down to 30. So within that row, all of these numbers inside are the p-values. I am going to look for where 3.1 negative, or well, the positive of it, it's all the same, where 3.17 would lie. So 3.17 would lie between these two values, and up here are my p-values. So that means my p-value is between 0.001 and 0.0025. So that's the unfortunate part about the table B, is that we don't get all of the p-values like we do in table A when we're doing our z-score. So it's between these two numbers would be my p-value, but we're doing a not equals to. We have a two-sided, so we're going to multiply each of those by 2, so taking 0.001 times 2 and 0.0025 times 2. So then my final answer is my p-value is between 0.002 and 0.005. Alrighty. And so in this case, if we were to continue this and do the hypothesis test, my alpha was 0.01, right? So either way, whatever I get, both of these numbers are less than 0.01. So I can still make my same conclusion of saying that I would reject the null if I needed to. But because this is not set numbers and we can just say the p-value is between a certain value, we usually like to use the calculator for finding that p-value. So when we're going to do that, we're going to go to second vars and we're going to look for TCDF and we're going to just put that in the calculator. Remember, we have our upper and our lower, or sorry, I think it's the other way around, lower and then upper, yeah. So we have the lower value in the calculator, that's this one. Then we have our upper. And then we have our degrees of freedom now for TCDF. So because this one was calculating greater than, then your lower is that number. So this is a different example, but we would just type in the 3.17. The upper is just a really big number because it's going to go on and on forever. And in this case, the degrees of freedom was 14. So if we put this actual problem in ours, then we would have, since we were doing a not equal to, we're going to put the lower as negative 1,000. We're going to do negative 317 as the upper. And then we have our degrees of freedom. And then they're going to multiply that finally by 2. So we get a more accurate p-value of 0.003. So now we have an actual number to compare to alpha. All right, so we've looked at how to find that test statistic and then the p-value. Let's go ahead and now we can run our hypothesis test because that's what we need for our do section. So same for process, state, plan, do, conclude. We're going to state the hypothesis, our significance level, that's the alpha, and define our parameters. We're going to check which inference procedure we're using and check those 3 conditions. We want random, we want 10%, and we need those 3 options for if it's large enough. We're either looking for a normal distribution for the population, a sample size greater than 30, or we're going to sketch out our data and show that we have no strong skewness or outliers. In the do, we're going to give the sample value, so x bar and sx. That needs to go in the do. We're going to find t, so that's my x bar minus mu over s sub x over square root n. And then you're going to use your, to find the p-value, so you're either going to say using table B, or we're going to use TCDF. And then that last thing we're going to do, make the conclusion. Remember, if the p-value is less than alpha, we reject the null. That means there is evidence for the alternative. And if the p-value is greater than alpha, then we fail to reject the null. There is not evidence for the alternative. All right, let's go ahead and take a look at the pieces again of our test statistic. So the first thing we're looking at is a random condition. So we're able to do this part of the test statistic if it's random, because I've done a random sample. I can use my sample value and compare it to my null value. Next, what I'm looking for, is it large enough? Because then I can use a t distribution. So now I can solve for t. And if the 10% condition works, then I know that this standard deviation is good to go. So this is our full formula for our test statistic. Once again, here we have our formula for our test statistic. And remember, when we're drawing out those curves, if we're comparing something to be greater than, we're looking for the larger tail. If we're comparing it to be less than, we're looking for the lower end tail. And if we're doing a not equals, we're doing the other tail as well on the other side. All right, so let's go ahead and run a one sample t-test for mu. The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 15 randomly chosen locations along the stream. Here are the results in milligrams per liter. An average dissolved oxygen level below 5 puts aquatic life at risk. Do the data provide convincing evidence at the alpha equals 0.05 significance level that aquatic life in this stream is at risk? And after we finish that, we're going to talk about type 1 and type 2 errors. So let's go ahead and run that test. First thing we're going to do is state. We're going to state our hypotheses. Mu is equal to 5. And we're going to check if it's at risk. And it's at risk if it's below 5. So we're going to do mu is less than 5, where mu is the true mean dissolved oxygen level in the stream. We're using alpha equals 0.05 as our significance level. Now let's plan. Our inference procedure is a one sample t-test for mu. Remember, we're doing a test now, not an interval. It is random. You selected it at 15 randomly chosen locations. It's very much like we don't really need to check 10% because there's a bunch of locations in the stream. So this kind of verbiage is fine. If you wrote that 15 is less than 10% of all locations in the stream, that's fine too. But it's not necessary, right? Like, think about your real world. Like, of course 15 is less than 10% because I can move over 1 little centimeter and now I'm at a different location, right? So we have an infinite number of possible locations. And let's check that normal large sample. We have a sample size of 15, so it is smaller. So we're going to go ahead and graph those. These are some ugly decimals, right? So we're just going to put it in a histogram, and it's almost symmetric, and there are no outliers, so we're good to go. And we can just graph that in our histogram. Alrighty, you can also, because we're going to have to find our sample mean and sample standard deviation eventually anyways, if you put all of your data points in your calculator, you can then create a graph, and then you can sketch the graph from your calculator. You cannot just write, I graphed it in my calculator. You still have to show your graph, but you can at least get the graph in the calculator to make it a little bit faster for yourself, since you already have to be putting these numbers in to find your sample values, your statistics. All right, so all three conditions have been met. We've stated our hypothesis. Let's go ahead and calculate. So remember, we need to find our X bar and our sample standard deviation. That goes from putting it in our list and then running the 1 var stats. Then we're going to plug it into our T formula. So statistic minus parameter over standard error. We get negative 0.94. We have a degrees of freedom of 14. Always list your degrees of freedom in your do, and we see that using table B, using our negative 0.94 T would give us between 0.15 and 0.20, and then if we use technology, TCDF gives us 0.1816, and this was a typo here. This is negative 0.94. Alrighty. So this 2 should have been a negative for some reason. Alrighty, but either way, put in the calculator, we get 0.1816. So either answer for your p-value is acceptable. Just make sure that you're writing using table B or using technology with your whole notation of what you put in the calculator. You cannot just write using technology, the p-value is 0.1816. Not allowed, okay? Make sure you're showing all of your steps, all of your work. Let's go ahead and conclude with that p-value. Our p-value is very much greater than alpha, so we fail to reject the null. We do not have convincing evidence of the alternative, which was that the true mean level in the stream is less than 5 milligrams. So there's our part A. Do we have convincing evidence? No, we do not. Part B said, given your conclusion in part A, what kind of mistake could you have made? Remember, a type 1 error means that I reject the null when I shouldn't, and a type 2 error means I fail to reject the null when I should have. So because we failed to reject the null, we could have made a type 2 error. We don't know, but it's possible because we failed to reject the null. So if we did, right, if we didn't reject the null, so we're assuming that the mean actually is 5, then we could make a really big problem here because we're saying that the aquatic life is not at risk when really it was. So our consequence for this, or in context, would be that would imply aquatic life in this stream is at risk, but we weren't able to detect that fact. So if we made that error and we failed to reject it, we're saying, oh, there's no risk, but really there was. So that's our context there. These are common follow-up questions when we have an FRQ that's not just the state plan do conclude. When we're doing a hypothesis test, it's going to ask you, what kind of mistake could you have made? And that's just based on whatever you answered in your other part. Alrighty, so just a reminder on what counts as doing the do. If you use the calculator, which is totally fine, just make sure that you're saying what you are doing and that you report everything. You want to say what T is, what your degrees of freedom is, and what your p-value is. That counts as the work. So if you have those three things, you're good to go, right? It's always helpful to have that T formula, so that's good to have that formula. But as long as you have the formula and then the calculator does everything else for you, you're fine. But you just have to state what you did with that calculator. You cannot just say, here's the calculator, and then here's my answer, because you're also not going to get yourself any partials, right? If you do the calculator and you do something wrong, there is no work to back it up. So you are not even getting a partial. You're just like, well, that's very wrong. So you're not even getting that piece. All right, so we've gone through our conditions again. We've done the test statistic and the p-value, and we performed a significance test. So we've hit all of the things that we need to today. So once again, it's the exact same thing as the hypothesis test we've already done. We just have a different normal condition. We have a different test statistic. Well, we have a different standard deviation formula. Our test statistic is the same formula. Statistic minus parameter over standard error. And then we run that test and determine if the p-value is greater or less than alpha. Alrighty, so we're going to solve, we're going to work on one sample means, and I'll see you back here next time for 2 sample mean intervals and tests. Have a wonderful rest of your day.